Okay. कोई और आने वाला? आज कई दिनों बाद आए हो तुम? बीमार थे पर मतलब समझ में नहीं आया ना इस कोर्स में. इफ यू मिस आउट अनलेस यू रीड द लेक्चर्स और लुक एट द वीडियो साइट पे तो अपडेट हो रहे हैं ना सारे. So that has been there, but anyway you have the week now. We can. Attendance mark. डेट और अटेंडेंस लिख देना ऊपर. Okay. So now we continue our discussion. Today, as I said, this will be the last lecture on chapter 3 of Lumley's book, which is about 50 pages. Probably one of the major chapters as far as physics of turbulence goes. And then the application to wall-free flows and walled flow comes in chapter 4 and 5. And that's when we will be looking at that, and maybe along with that we may try to look at the equations from Pope's book also for those two cases. Okay. Now here in this chapter, so one thing I would request you to do is in the break, please go through this chapter 3 entirely again. So that, because we have been going for a long time on this chapter and some of the earlier part we may have missed now. So read the entire chapter in its entirety now. It will take you some time, but then because we have introduced so many new concepts, Taylor microscale. So we introduced it for velocity, now we will today call it for temperature, etc. So look at all those concepts, try to rework at many places. He says show it like this, so then try to work them out. They are simple, this thing. So read this chapter fully again, chapter 3, because that is what will then give you some more feel for the subject. Okay. So now in the last class, उसका क्या हुआ? थोड़े हर्षल नहीं दिख रहा. We looked at the equation for vorticity fluctuations or the energy term which becomes associated with the vorticity fluctuations, and this was the final form in which we were able to derive this equation. Now the dynamics of the fluctuating vorticity is representative of dynamics of other axial fields in turbulent flows. So just as we have the equation for vorticity, if there are some passive scalars, then their equations could also be often represented in this form, as we have got the equation for vorticity. And one example of this is if we have magnetic field lines in a conducting flow are stretched by Sij prime very much like the vortex lines. So for example, if there is a magnetic field and the magnetic line, magnetic field of force line is represented by a line, then just as the vorticity is stretched by the fluctuating strain rate, similarly magnetic field lines will also be stretched by the fluctuating strain rate in a similar mechanism if the flow is turbulent. So, and here what we find is the main crux of this equation is that the amplification of fluctuations of omega I prime are kept in balance by the dissipation. The production of omega I prime takes place because of the stretching of by the Sij, the fluctuating strain rate, but that is kept in balance by the dissipation field. So, therefore, it does not allow them to be magnified infinitely. Now, if the quantity or the physical quantity is something other than vorticity, then basically instead of nu, the diffusion coefficient will be gamma corresponding to diffusion of that quantity. So, instead of nu, we will get a similar equation. Instead of omega I prime, we will have the fluctuations of that quantity. So, for example, if it is a magnetic field, instead of du I prime by dx, the omega I prime, we will have h I prime, the fluctuation of the magnetic field instead of omega. So, we will have an equation like, for example, in magnetic field I am not writing it will be h I prime h prime h j prime Sij prime is equal to, but now on the right hand side this coefficient will become the diffusivity of that quantity. For example, in temperature we get thermal diffusivity K by rho C, and for temperature we will derive the equation. But so, for example, if this is magnetic field, then instead of nu there will be some gamma corresponding to the magnetic field. So, we will have gamma times h I prime or h I prime h j prime, whatever it is. So, now one more thing will happen, because gamma differs from nu, the dissipative scale of the quantity will differ from Kolmogorov scale for velocity. So, the length scale at which the dissipation takes place was a function of nu, square root of or nu upon epsilon to the power 3/4. Now, instead of nu there is gamma. So, therefore, the dissipative length scale for that quantity, if gamma is not the same as nu or not of the same order, will be different. Okay. So, now let us say we are talking of, let the quantity be the magnetic field, and let h prime be the fluctuations of the magnetic field, and gamma m is the diffusion coefficient. So then what we will have will be, the equation will become hi prime hj prime Sij prime is equal to gamma m partial hi prime So this is the equation we will get for the magnetic field, assuming we are doing in same order of magnitude analysis and the two dominating terms will be of the same order. So this is the sort of physical field which we get for the magnetic field. Now, yeah, Sij is still the velocity fluctuation, the same thing, because this is magnetic field in a turbulent flow. See, this is, so magnetic field there is like a passive scalar, and we are assuming it is not affecting the velocity field.
So what do you mean by like
Passive scalar, by that what I mean is that the equation, the passive scalar does not come in the velocity equation. So the velocity equation stays the same. The scalar does not affect the equation for velocity. And an example of that is when we look at the temperature field. As we will see now, if the buoyancy term is not important, then we can treat, for example, if there is small temperature change such that density is not getting changed at all, then the velocity equation stays the same, but from the temperature equation we can find out what is the variation in that temperature. So there is a one way, it is not a two-way coupling. Velocity is affecting the magnetic field, but magnetic field is not affecting the velocity.
So whatever we are talking about here, the velocity of
So it's a conducting fluid, electrically conducting fluid in which you have a magnetic field.
okay,
It is some.
the magnetic field also being transported.
It is being transported. That's why we have this Hi prime, Hj prime. So magnetic field is being transported, and we assume its equation is similar to the temperature equation, and then the magnetic field equation, the dominant terms in that, when we look at the fluctuating part, or when you are looking at the fluctuation of something like the entropy vector, we create another vector which is the magnetic field square. So those fluctuations will have a similar form.
How can we take the magnetic field to be a passive scalar? Like it's a vector.
No, it is clearly a vector, but then does it affect the flow? So then you will have to derive certain conditions under which, so what will happen is that when you write the total equations, it will be affecting the flow. You non-dimensionalize those equations. So a coefficient will come in front of the magnetic term. So when that coefficient is much less than 1, then we can assume that magnetic field will just be a passive scalar. So when you have situations like this, that's a very good question. You have a complex field, you write the equation for the complex field, including all the terms. And then you do the non-dimensionalization of that equation, a proper non-dimensionalization where each term is non-dimensionalized according to its own order. So you don't have, so all non-dimensional quantities always will be of order 1. You don't non-dimensionalize, that non-dimensional quantity always stays 0, because then that is not a proper non-dimensionalization. So then the coefficients which come in front of each of these terms will define how important the term is. Okay? Yeah.
So in last lecture we have shared the relation between Sij prime and del omega prime by del st.
Yeah. We have
Sir, you have written Sij prime 2 times.
where in this one, oh here there will be Sij, it will be 2 times. I think I've,
It is starting.
हाँ नहीं, यहाँ पे भी मैंने गलती कर दी. यहाँ आई थिंक यहाँ पे Sij प्राइम 2 बार होना चाहिए था मैंने वो. यहाँ तो 2 बार, 2 ही बार तो आएगा, नहीं आएगा. एक मिनट को, आई जे इट अपीयर्ड ओनली वंस, ओमेगा आई ओमेगा जे Sij. ओके ओके, तो यहाँ पे भी फिर एक ही बार है. यहाँ तो एक ही बार है. ठीक है, थैंक यू. ओके, Sij तो एक बार. आई वाज थिंकिंग ऑफ द राइट हैंड साइड, इन द लेफ्ट Sij हैज टू बी. then only you get a scalar. ठीक है? Sorry. In fact, what I wrote is dimensionally is tensorally totally incorrect. I have got I coming 3 times, J coming 3 times, so obviously this expression is wrong. So maybe let me just चलो उसको काट दिया, ठीक है, कट प्रॉपरली. हाँ हाँ कर लो, पूछा मत करो, चुपचाप चले जाया करो यार. Okay, so now let we want to work out the dissipative scales for the magnetic field. So here what we will do is we will look at this equation, and from here we will try to find the dissipative scales. So let the dissipative length scale for Hi prime be eta m. So we have a Kolmogorov scale, but this is for the magnetic field. Let's write it as eta m. And let RMS of Hi prime be Hi prime RMS. So that's the scale which we are saying. So now in this equation what we will get is let me not use I here, let me just use HRMS, this is the order of magnitude, HRMS square times Sij. So Sij will be U prime RMS upon lambda, the Taylor scale. This is equal to gamma m HRMS prime square divided by eta m square. So again now we are doing an order of magnitude analysis. Let's try to understand whether Hi we say is H prime RMS. So H prime RMS square, and Sij prime is equal to, if this is well correlated, and we'll talk a bit about this, will be U prime RMS upon lambda, and this will be equal to, basically we are trying to get eta m is equal to gamma m times H prime RMS square upon eta m square. And from here what we get is, and if we work out, we'll be able to show and for this we have used U prime RMS upon lambda. This was equal to, and we have also used eta is equal to so we use U prime RMS upon lambda is epsilon upon u to the power half. That was the basis, and then the Kolmogorov scale, because we want to find the ratio of these two scales, it turns out is equal to square root of gamma m upon nu to the power half. Okay, and this is something like gamma m upon this is something like an inverse Prandtl number. Nu upon alpha is what we call as a Prandtl number, where Prandtl number we use for thermal coefficients. So nu Cp by k, तो nu upon k, रो भी होगा, nu upon rho Cp upon nu k upon rho Cp, basically rho Cp upon यही होगा ना, nu नहीं nu k by rho Cp होता है बस, that's what k by rho C is nu, is gamma or whatever, alpha is equal to k by, we call it alpha actually. So this is what you will get, and this is basically like an inverse Prandtl number. Nu upon gamma m, nu upon alpha is the Prandtl number. So this is like a Prandtl number, you can call it for magnetic field. It's basically a ratio. So it's like inverse of Prandtl number. Now there is one thing we have to see, and that's of importance. So this is the first thing, and what what if so if this ratio, if this gamma upon nu, if the coefficient of diffusion of the magnetic field is much less than 1, and this tends to happen in gas clouds. In gas clouds, gamma upon nu is of the order of something like 10 to the power of -8. So if this is much less than 1, then what we infer is that eta m is much less than eta. So that means if suppose this was an initial stretch of filament and these dotted lines, they represent lines of constant h. Suppose if there was a film, if there was a blob of this type, now what happens is eta m is much less than eta. So the vortex stretching, it will keep on stretching these magnetic lines of force to a very thin filament, and this notionally will change. So what we will have is, and these magnetic lines of force will become constant lines of force, will keep on becoming thinner and thinner. So here what happens is the eta m is at a much smaller scale. So the scale reduction of the magnetic lines continues to a much lower level, and the initially circular blob stretches into a thin filament, which are then mixed by Sij prime. So in interstellar gas clouds, where nu m upon gamma and gamma m upon nu is of the order of 10 to the power of -8, the smallest magnetic lines are much smaller than the scale compared to eta. And a physical example of this happens when you have a paint, and in a paint you put many colors. Then the diffusivity of the paint by itself, the colors which you put, is much less than the diffusivity of the mixing fluid. And there what you find is that before, when you mix the paint, first the individual paint colors go into very thin filaments and then they get mixed. So somewhere you can think of that as a physical example of this quantity where we have this sort of a mixing which takes place, And so, in this sort of a mixing, the magnetic lines, the length scale associated with them is much less in these situations as compared to the dissipative scale of turbulence, of the physical turbulence. The magnetic turbulence line, or whatever you may call it, is at a much smaller scale. Now, a complex situation happens in the opposite limit. In the opposite limit, when gamma m is much bigger than nu, then what will happen to eta m? Eta m, the dissipative scales, will be larger than the dissipative scales of turbulence. And so, therefore, these smallest scales of that field will not be in the dissipative scale, but it will be somewhere in the inertial scale of turbulence. And for that, that means a different scaling will have to work, and we will see that when I talk of temperature. You can, there's a nice paragraph, you can read that in Lumley's book, but I'll talk a bit more of the other limit when we talk of temperature. Because then we have to do the scaling again, and there the whole scaling will change. So, this actually I was planning not to do this small section on magnetic lines, but one of the students told me he was interested, so that's why then I thought let me cover a bit of this also, so that at least you get a feel of what is going on. I don't know how much it helps you in your understanding, but at least there is some. So, now let's try to focus on temperature fluctuations, and we will look at the case where temperature is a passive scalar. And let me rewrite the things which I said at the start. Passive scalar implies one-way coupling of theta and u, that is, and velocity, that is velocity field not affected by theta, but theta okay. Now, the equation for this turns out to be the temperature equation. Let theta be the temperature. So, the equation for theta in this case, what would you expect? Partial theta by partial t plus uj d theta by dxj is equal to gamma वेलोसिटी वी वेक्टर लिख देते हैं, या तो मैंने वी कॉमा नहीं, वो वी पूरा दिख नहीं रहा था, वी वेक्टर लिखा था, विच इज ऑल्सो इक्वल टू वी जे. If I write it in tensor notation, this will become v sub I or v sub j, whatever, theta and v. Right? No, there's no prime right now. I just wrote for temperature. By mistake I put the prime there, so which I did not intend it to be there. Prime will come, of course, when we talk of. So this is the equation for. So this is the equation for temperature, which we have, of course, in a. This is a simple equation. There may be source terms in temperature also. There may be radiation and other terms if they are there, and this will come. Basically, this term is the conduction term which you get from Fourier's law of heat conduction. So this is basically that term is there. So let's look. Now, of course, what will we do if we have to this? We will write theta as mean theta plus theta prime, the mean and the fluctuations. And then what we do? We First thing will be we write the equation for theta prime. Do you all recall how we will do this? कैसे करेंगे? अभी ओमेगा का तो आज लिखा ही होगा इक्वेशन. कैसे करेंगे? पहले इसका मीन लेंगे. We first write the mean equation for mean theta and then expand this as theta plus theta prime, mean theta plus theta prime, subtract the two, that will give us the equation for theta prime. ठीक है? कभी तो पूछेंगे ही, अभी नहीं पूछेंगे तो होमवर्क में पूछ लेंगे, एग्जाम में पूछ लेंगे, कहीं पे पूछ लेंगे. ये वाला इक्वेशन सिंपल है. ये तो अब तक नाउ this you should become experts in doing this. Okay, and then what we do is, this is the first step. Second, what we do is we write the equation for mean of theta prime square. तो ये कैसे करेंगे? पहले इक्वेशन ए है ये वाला, we multiply all the terms by theta prime and then we take the average of that, so we will get an equation for theta prime square. Again this you should be able to do it. Okay, and then in the limit, so this equation will become partial theta prime square by partial t. वो half will come in because when you have a theta prime d theta prime by dt, when you combine that it becomes a half comes. So either you can finally remove half from all the terms and multiply by 2 wherever the half is not coming. It doesn't matter, it's just a scalar. Okay, what is the second term which you expect? Convection. So how, what is the form of the convection term? Mean of uj d theta prime square by 2 by dxj. That's how we are seeing the trend in all equations. So the second term will be mean of uj d by dxj of theta prime square by 2. And this is equal to, now I'll write the final equation, minus d by dxj of half of theta prime square uj prime minus gamma d by dxj of theta prime square by 2. Then we have a term minus theta prime uj prime d theta by dxj minus gamma this is the equation for what you can call as the kinetic energy associated with temperature fluctuations. Actually, I should not be using the term kinetic energy, but it's theta prime square. So, of course, we have the equation we derived. We have derived two more equations of similar quantities, one for the kinetic energy and one for the vorticity. And those equations were much more complex than this. This equation is really relatively much simpler. Yeah.
It's not like we are getting any new information by forming this equation. Then, and neither is delta t square a physical t prime square a physical quantity. So why are we doing this?
Well, we are doing this because what will happen is that in this particular case, probably this is just to analyze the temperature turbulence, the turbulence associated with the temperature fluctuations. What is that? And
Theta prime equation, right?
that is a theta prime equation. So now theta prime equation is the fluctuating part, but to get to those scales may not always be. Why are we anyway? Then your similar question is, why should we write the Reynolds stress equation?
That has a physical meaning, right?
So this equation, the physical meaning of this will come is if you look at the theta equation, mean theta equation. then in the mean theta equation you will get this term theta prime uj, which is what you call as the temperature flux. And when we write this equation, this also comes into picture. So, there is an equation for heat flux, and if we have to solve the equation for heat flux, the temperature, this theta prime square comes in that equation. So,
There is no such thing as this, right?
there is
There is no physical meaning of this, right?
physical meaning of theta prime square. Yeah, probably temperature square, there is no physical as such, we don't use that. And in this also, the next step what I am going to do is, when I talk of a situation, when I talk of homogeneous and stationary flow, what will you be left with? You will be left with only these two terms. So, in fact, all theta prime square will go away there also. When I talk of a homogeneous means, basically the derivative of mean theta is not 0, but all other derivatives of the turbulence, they are 0. So, that is the next step which I am going to do. So, yeah, in that sense you are right. But then what happens is, if I talk of we will talk when we do the modeling part of turbulence, and when we have equations containing temperature, then theta prime square turns out to be a term which is there in the equation. So, we have to solve an equation for that if we want to go to that level, or we write a model for that. So, that in turbulence modeling we will probably cover some of that. So, here let this term be called T1, let the second term be called T2 and T3. Now, T1 term is the rate of change of theta prime square controlled by turbulent and molecular transport of theta prime square. Let me just get this term. T1 is this term. So, this is basically a transport term, partial by partial xj, as we have said, and this contains two terms. One of them is how theta prime square is being controlled by the velocity fluctuations, and this one is how the turbulent part, because there is a theta prime square uj, and in the second one we have gamma which is coming there. So, the molecular transport of theta prime square. Gamma is the molecular term, molecular transport coefficient of theta prime square. So, this is just a transport term, and once again, if on the surface if we introduce, it will just be redistribution. It could go to 0 on the surfaces if I use the Gauss's divergence theorem and try to work that out. Okay. The second term which is there, this is the production term, because now this is not a transport term, there is no d by dxj. So, this term basically is like the turbulent production term of in kinetic energy equation we had. So, this leads to the production of theta prime square. And the third term which we have basically is the molecular dissipation. And again this is production of theta prime square, this is dissipation of theta prime square. Now, in steady homogeneous flows, the equation reduces to, so once we talk of stationary or steady flow, this term goes away. All the gradients, it's homogeneous. So, therefore, of all the averaged quantities, fluctuating quantities, this goes away. D by dxj of fluctuating quantities goes away. So, we are left with only this, and d theta by dxi, this is a mean gradient. So, this can still be non-zero. So, yeah. there is no, okay. So therefore the equation reduces to T2 plus T3 is equal to 0. So what we get is this equation, therefore in equation reduces to minus theta prime uj prime d mean theta by dxj is equal to gamma times and this is something analogous to P is equal to E for turbulent kinetic energy. That the production of theta prime square, which is given by this term, is balanced by the dissipation of theta prime square. So we get a similar form which we got in the vorticity equation also, and we got in the turbulent kinetic energy. So now if the flow has only one length scale and one temperature scale, let the temperature scale be theta prime RMS, then theta prime uj prime, this will be of the scale times u prime RMS, d theta by dxj, this scale will be theta prime RMS upon the length scale, and epsilon theta will be equal to theta prime RMS. So now let me call this as epsilon theta. So this will be equal to, so this is basically epsilon theta will be of the scale of production, which is equal to theta prime RMS u prime RMS times theta prime RMS upon L. So this will be of the order of theta prime RMS square upon u prime RMS upon L. And this, if you recall, this is similar to when we did a turbulent kinetic energy equation. We said dissipation was u cube upon L, which means it gave us the rate of transfer. What was u cube? U cube could be interpreted as u prime square divided by L upon u. L upon u is a time scale. So now here again you have a similar thing, theta square divided by the time scale, which is equal to L by u. So this is analogous to epsilon is equal to u cube upon L. So basically here what you are saying is that epsilon theta represents rate of transfer of temperature fluctuations from large scale to small scale. Similar to epsilon is equal to u prime RMS cube upon L, which was equal to u prime RMS square times u prime RMS upon L, and the second term was 1 over T. And similarly, we have theta prime times u prime RMS upon L. So what we have is dissipation of temperature, which is of. Now, so what one can do here is one can talk of, we have something missing. We have this. One page which is missing. Let me just see. Okay. So now we have this dissipation term was gamma d theta prime. Now if we introduce a Taylor microscale for temperature, and let us call this microscale as lambda theta. So what we say is let delta theta prime by delta x1, delta theta prime by delta x1, this average be equal to 2 times theta prime square upon lambda theta square. So we have introduced, basically we are trying to work out this term d theta prime by dxj, d theta prime by dxj. So this will be equal to d theta prime by dx1 whole square plus d theta prime by dx2 whole square plus d theta prime by dx3 whole square. And to simplify things or to understand this, what we do is we study isotropic fluctuations to get an order of magnitude here, which implies that d theta prime by dx1 square is equal to d theta prime by dx2 square that with variation things don't change. So therefore putting this, what we get is see, what we are trying to do is, just as we had in the Taylor microscale for velocity, the dissipative terms, u prime RMS is not the right scale for the dissipative velocities. And similarly, this L which we got is not the right scale for the dissipation. So what we do is, we say if the dissipation velocities, we use u prime RMS as the velocity scale, then we introduce the scale lambda so that this ratio becomes correct. So similarly we are doing here, we have introduced a Taylor scale lambda theta for temperature. So now this term must be of the order of left hand side, which is the production term, and left hand side we have already worked out minus theta prime uj prime d theta by dxj. This is of order theta prime. You pen me, there is a bit of, let me try to recalibrate this. Theta prime RMS square u prime RMS upon L. So now we put these two equate. And what will this give us? This theta prime square will be theta prime RMS square. So when we equate these two, the two theta primes will go away. Okay. So you will get an equation for lambda theta square or of the order. So you will get for here, once you equate these two, what you will get is lambda theta square is of the order of 6 times gamma L upon u prime RMS. I think I have done my 6 gamma L. ठीक है, this is what you will get. वो 6 वो 2 था ना एक, और तीनों जब सम किया वो 2 क्यों लिया, मतलब दैट इज हिस्टोरिकली बीन टेकन एज 2. वो सी हमने क्या किया, इस वाले में 2 ले लिया, तो उस 2 से 2 प्रोबेबली इज टेकन बिकॉज इट थीटा टाइम्स थीटा प्राइम बाय x1 को अगर हम थीटा प्राइम अपॉन लैम्डा थीटा लिखते हैं तो आई डोंट, मतलब दिस 2 इज probably for historical reasons. Corson did this first time in 1951 and he put this factor of 2. So वैसे ये सब 2 absorb हो जाएगा because everything will be go in the correlation coefficient, तो square root of 6 हो जाएगा क्योंकि अभी lambda जो lambda theta square आया है that is this, so that means lambda theta will be of the order of थोड़ा 2 मिनट छोड़ देता हूँ, 1 मिनट इसमें देख लो. ठीक है. Yeah. RMS. Yeah. So lambda theta eventually takes this form, and what you can then do is you can relate lambda theta square upon lambda square, and this turns out to be equal to 6 times gamma upon mu, because lambda is equal to Reynolds number to the power of half, so lambda square, or to the minus half, so lambda square will be nu upon ul. So once you do this, what you will get is this, and from here what we get is basically this implies lambda theta upon lambda is of the order of c times square root of nu upon gamma. So this is the length scale. Again, lambda theta is probably not the right length scale, doesn't represent any particular lambda. But then the last thing which stays, and let me continue for 5 minutes or 10 minutes more today. Yeah. हाँ, तो वो C, मतलब वो C को 1 order 1 हो जाएगा. It's of order 1, just to show that it is not very large. It's not 10 to the power of 4 or 10 to the power of 5. Now, one more thing stays, to get the, इसको क्या हो रहा है, to get the dissipative length scale for theta prime, That means the length scale at which temperature dissipation is taking place. Now, for this, what happens is that we will need to go to the, to get to this dissipative scale, we need to look at, and will not, and equation for just as we needed the equation for vorticity, we will need to get the equation for eta theta, the temperature dissipative scales. We will need to write the equation for the derivative of temperature. See, vorticity gave us the equation for the dissipative scales, and here what we will do is, will not write the equation, we will just show that this will take the form, and this is again now weird. So, this is the analogous equation, will not be, in fact, actually this is, I made an error here. This is similar to the vorticity equation. If gamma is bigger than mu or of the same order, then eta theta will be, the dissipative scale is less, and this we have seen for the magnetic field. And here what happens is, then this equation will become d theta prime by dxj will take the be of the order of the smallest temperature scale by eta theta, smallest temperature scale by eta theta times the velocity scale by eta, and this will be equal to gamma times the temperature scale divided by eta theta square. क्या हो रहा है इसको, अभी बता रहा हूँ, अभी एक मिनट, आई जस्ट कम. Which one? The third term. This is v eta, the smallest velocity scale, because which is equal to u prime RMS upon lambda. V eta upon eta, that the smallest velocity scale by smallest length scale, and smallest temperature scale by the smallest. So now we are not using any Taylor scales here, just going by the right term. So this becomes equal to gamma upon, put a nu here, so we get nu upon v eta eta, and this is of order 1. So what we get is eta theta upon eta is of the order gamma upon nu to the power.
What did theta theta mean?
Eta theta is the smallest scale for temperature. See, just as we got the smallest length scale, that means temperature ka agar, of course, we don't talk of a filament of temperature just as we had in the magnetic lines of force. So, the smallest length scale at which the temperature fluctuations take place. So, if gamma and nu are of the same order, they are of the same order. But if gamma is bigger than nu, then the temperature fluctuations take place at a smaller length scale as compared to the velocity fluctuations. So, that is what we are trying to just but so this we had done for the, we didn't do it in this way, but the magnetic lines of force also we showed that this was equal to square root of gamma m upon nu there. Okay. Now the last thing, and that is, let me just finish it so that, and you can read it more from the book. But if gamma is greater than nu, then eta theta is larger than eta. Now, eta is the smallest scale for velocity, eta theta is the scale for temperature. The smallest temperature scale is bigger than the velocity scale, smallest velocity scale. So, now in this case what happens is that eta theta lies in the inertial subrange. It is not in the dissipative range, not in dissipative range. So, now the Sij prime which affects theta is a function of epsilon and eta theta, not of nu. See, earlier what we said was the velocity scales, we determine the smallest velocity scale by saying they depend on epsilon and nu. But now the temperature scales are not affected by nu, they are bigger than that. So, therefore, the Sij prime which affects theta, the smallest scale is a function of only epsilon and whatever is the smallest length scale for temperature. And here what you can then show is that this Sij prime goes like epsilon to the power of 1/3 and eta theta to the power of -2/3. This is pure scaling argument, that it depends on one velocity and epsilon. And from here what you get is theta eta, the smallest temperature scale, divided by this times this is the left hand side equation. This goes like gamma times theta eta square upon eta 4. So, this I am getting from left hand side of theta prime equation. This is the right hand side of theta prime equation. And this leads to a scaling of eta theta upon eta goes like gamma by nu to the power of 3/4. Yeah. Yeah, theta eta, that means temperature smallest scale. थीटा ईटा उसका स्क्वायर, बिकॉज वो लेफ्ट हैंड साइड में ये आएंगी, वो ये दो टर्म्स आती हैं उसके कारण डी, एक मिनट रुको, ये आती हैं थीटा प्राइम स्क्वायर डी थीटा प्राइम बाई डी एक्स जैसे. See, this becomes theta at the small scale, smallest scale of temperature. What is this? This is theta eta. This is by eta theta. So these two terms. But Sij now is not the smallest scale of velocity, but actually because here the smallest scale of temperature, it scales like epsilon to the power of 1/3 times eta theta to the power of minus 2/3. So, the left hand side becomes theta eta square upon eta theta square times epsilon 1/3 times eta to the power of minus 2/3, and the right hand side is still gamma times theta eta square upon eta square whole square. So, therefore, you get this, and from there the scaling therefore changes, and what we get is that, so this is for the case where the thermal coefficient is larger than the velocity diffusion. So, anyway, this just I have gone maybe a bit fast. What I have suggested to you is that in this vacation, please read through the full chapter 3 of Lumley, because we have covered so many things starting from velocity. It's a big chapter, probably the main chapter which talks about the physics, and we started from something and we have gone till the end, gone up till here. So, read the full chapter carefully, maybe 5-10 pages in a day or something. Try to absorb these things, and this also, these arguments, some of this were not given in Lumley's text, and this scaling, I think he just presumes that you will get it. He just writes it like this but doesn't explain the full thing. So, this you can have a look at it and you will then be able to appreciate. Try to look at the problems of chapter 3 also. There's 1 or 2 sections we have not done, but other than that we have covered pretty much the whole of chapter 3. There's a last section on buoyancy production. I am not covering that. So, just the last 2 pages of chapter 3 text have not been covered, where he talks of buoyancy and production due to buoyancy. अच्छा, आज का होमवर्क हो गया. एक अटेंडेंस शीट भी थी, वो सबने मार्क कर दिया. Has everyone signed this?